Now today we're going to be more relaxed. I've been giving you lots of things, been covering lots of work, and so we're going to focus today on distributions, random variables and distributions. And I'm going to talk also about start talking about applications. My applications are in football and crime, so these are the two things I've worked on using some distributions. Okay, and also there's not a whole lot of questions afterwards. I will set so you have time to catch up on the previous work, but I will set one question as well. Okay, so we covered this yesterday, random variable as a function. So the crucial thing is the random variable is a number, but we can also think of it as a mapping from our space of possible outcomes. Whoa, what have I done? Sorry, I'll click this on again. To the real line. So it's a number. So our random variable, x, maps to the real line. It's a number. So we're now going to be starting playing with numbers. So it might be, for example, the total number of heads we flip. Now, okay, there's a whole lot of stuff here. But these are important. They're basically the measures, if we have a random variable, of its expectation, how big we think it'll be on average, which is the values it can take on weighted by their probabilities, and its variance, which is how much it varies around the mean. Standard deviation square root of the variance. Now, sometimes I put in a suffix there, but often we can leave it out. It doesn't, sometimes it's useful to be clear what random variable we're talking about. And the other thing to remember is this strange use of a little x, a big X, and a little x. And essentially, the big X is the random variable. It's before we observe it. It's the unknown quantity. Whereas actual observations, we give little x's. So that's why we talk about, we use this strange thing of saying the probability of x equal x. So that means the probability of a random quantity equaling a specific value. Okay, so that's just some notation. On the variance, it's important that to note that the variance, the easiest way, usually that's what it's defined as, but it's usually easier to calculate it as the expectation of the square of the random variable minus the expectation all squared. So the expectation of the square minus the expectation all squared. And because this is often quite easy to calculate, we just calculate, we look at the distribution for x squared. And this is the proof of why that works. We just expand this square and we get an xi squared and then a 2 expectation of xxi plus an expectation of x all squared. And then when we take the summation through there, we end up with another expectation of x. So we essentially end up with twice expectation of x squared plus expectation squared, and that gives us just a single one of these, and we end up with a nice formula. So that's a standard formula, very useful. Okay, so now we mentioned some distributions. The simplest distribution is just an event 0 or 1. It might happen with probability p, or not happen with probability 1 minus p. And we traditionally say give it value 1 if it happens and 0 if it doesn't happen. So that's the simplest distribution there is, really. Bernoulli trial. It's got mean p, variance p times 1 minus p, and we'll be using that a lot. Okay, a binomial is when we do a lot of Bernoulli trials. So we flip a coin lots of times, or we do anything many times. And as I described yesterday, the probability of a particular sequence is p to the x 1 minus p to the n minus x, but there are n choose x such sequences, the combinatoric, and so our overall density looks like that. And that is mean np and variance np times 1 minus p, which we'll prove later. We'll prove those later. That's quite straightforward. Okay. Oh, now we're getting on to new stuff. Here are some binomial distributions. I got them off Wikipedia. So that's why they're in German for some reason. Wahrscheinlichkeit. I'm sure it means probability in German. So this is a German graphic. I don't know why it's a German graphic, but so this shows, for example, a binomial distribution for n equals 20. So if we do 20 experiments, if the chance of each one succeeding is 0.1, 10%, this is the distribution of the possible results. The most likely one is to get 2 successes. You'd expect that. That's also the expectation, the average, because each of these has got a 1 in 10 chance of succeeding. But we could get none at all. Looks like about 12% chance of none at all. 1 is almost as likely as 2, and 6 and 7 gets very unlikely indeed. This is the distribution we'd expect. The most likely one is 10 successes, 10 heads. 8 and 9 and 11 are almost equally likely. It goes right down 15, 16, 17. And if we've got a 80% chance of success, we most likely is 16, that's the expectation as well. We could even get 20. 20 is almost impossible with this. It's possible with the flipping a coin, but not very much. Okay, so we can calculate those, and in the practical, we've asked the question from yesterday, asked you to use the random bin binom, I don't know, function. What's it called? Random.binomial. And that allows you to sample from the binomial, but also generate these distributions, to find these distributions. So it's all in there to use it. Okay, so, yes, now this is an interesting one. Let's do, no, actually, I won't go straight to that. I will do this. Let's pretend we were doing a binomial, we were playing a lottery. So we had a lottery which had, there was, the interesting, we've got n chances of winning. So this is sells n tickets, but P is very small. So P is very small. So the expected number of winners, is just NP, and we give that, we say that's mu. That's the expected number of winners. NP is mu. Now, we can just then define P as mu over n, if that's fixed. So, and if we then substitute that in the binomial formula, we got, remember the binomial formula says n minus x factorial x factorial, and then it's P mu over n to the x, 1 minus mu over n to the n minus x. And what we should do then is see what happens as n goes to infinity. What happens to that formula as n goes to infinity? And okay, this is what I'm going to try to do. So if I can get this right. We can take an x factorial outside, and then we've got an n minus 1, n minus x plus 1, divided by n. If we do it, that's the n to the x there. If we take the n to the x, we get an n for each of these terms. We've got a mu to the x there. And then we've got a, so that's got rid of that. And then we've got a 1 minus mu to the n to the power n, and a 1 minus mu to the n to the power x. So that's just an identity so far, a nice identity. Now, what happens when n goes to infinity? That goes to 0, so that goes out to 1. N goes to infinity, all of these start cancelling out, or each term goes to 1, so all of these go out. Now that is just goes to e to the minus mu. So we end up with this beautiful formula, mu to the x over x factorial e to the minus mu. And that is the Poisson distribution. So we've derived the Poisson distribution as a binomial when you've got very many chances of something happening, each with a very small chance. And the Poisson is my favorite distribution. So that's the maths. That's just what I've said. The Poisson is a beautiful distribution. It's got mean mu, which we'll prove in a minute, variance mu, and it's very widely used for count data. We're going to use it a lot in our examples in our practical statistical modeling, because it's the one I've used most in my career, because if you're analyzing any events, counting anything, counting how many crimes there are, how many goals there are in a football match, how many cases of disease, how many mothers die giving birth, how many anything, which is most of what we do, you need a Poisson distribution. So it's very common. So I'm actually going to do a little bit of, before going on to, I'm going to do a little bit of break, to illustrate this, to show some of the work that we have done in this. Okay, here we are. Okay, so I'd like to show some applications of this. So this is one project I have, which I don't like football, but I was asked to predict football results. Because it turns out that the number of goals in a football match follows a Poisson distribution. Because if you think of a football game over 90 minutes, there's hundreds of chances to score a goal. Well, there's many chances. But at each one, there's a very small chance. Every minute, there's a chance. So it ends up that actually the variability in a Poisson is Poisson, and it matches the data really well. So the point is, though, what is the mean of the Poisson distribution? What mean should you use? What you want is the expected number of goals that a team will score. Okay, how can we get at the expected number of goals a team would score? Now, this is the English Premier League, I think 3 years ago. 3 years ago, you can see, and this was the state with one match to go. So it's almost at the end, so this must have been in May, with one match to go. Now you can see this is before Manchester City started spending all their money on players, so they're not doing so well. Before they had a huge, so it's Manchester United at the top, Liverpool doing well, and this was when these teams were still in the Premier League. So we can see, this was from a few years ago. Now, how can we work out what's the expected number of goals for each score to score? And what I'm going to describe now is what the sports betting companies do when they try to set the odds for a football match. So this is a really popular use of statistics now. Okay, what they do is to work out an attack strength for a team, so how good their attack is, and how weak their defense is. Now, if you wanted to summarize how good a team's attack was, what's the simplest measure? Just how many goals they score. How many goals they score. So what they did is look at how many goals each team has scored. So Manchester United had scored 67, Liverpool had scored the most, 74, right down to poor old Middlesbrough, only 27. And the average is 46. So the average number of goals is 46. So if we take a ratio of this over 46, we get a measure of sort of the strength, the quality of the attack. So top is Liverpool, who score 61% more than average. Bottom is Middlesbrough, who only score 59% of the average number of goals. Now, if we want to measure how bad a team is in defence, we look at how many goals they've let in over the season. Again, poor old West Brom have let in 67, whereas the lowest here is Chelsea, have got the best defence, they've only let in 22. So if we divide that by 46, because the average number of goals scored is the same as the average number of goals let in, there's sort of symmetry, we find that this has got the smallest weakness and West Brom has got the most weak defence. And this is what's done in the sports betting companies each week to assess how good the teams are. Okay, how can we use this to work out a mean for a Poisson distribution? Okay, one of the games was Hull City against Manchester United. Hull were nearly down the bottom, Manchester United at the top. But Hull were playing at home, and there's a home advantage if you're the home team. Now, how we work out how many goals we expect a team to score is quite a simple formula. On average, in the Premier League, a team playing at home scores 1.36 goals. So the 1.4 goals about on average. Now, but Hull is not average. Their attack strength is only 0.85. So they only score 85% of the average number of goals. So we downweight that by 0.85. But then they're not playing an average team. They're playing Manchester United, which has got a very low defence weakness. And so we multiply that up as well. And we get that Hull, we expect them to score 0.6 of a goal. Yeah, okay, you can't score 0.6 of a goal, but that doesn't matter. It's an expected value for 0.6. And similarly, Manchester United. Now, if you're playing away, you only on average score 1.06 goals. The big home advantage, about 30% difference. Now, Manchester United's attack strength, they've got a very good attack. They score 46% more goals than average, so we multiply that up. And Hull has got a terrible defence. They're very bad in defence. They let in a lot of goals, so we multiply that up again. And we see that Manchester United is expected to score 2.12 goals. So it's a very uneven match. So now, what do we do with those expectations? We use the Poisson distribution. Because if we put those numbers into this formula, if we put these numbers in for the mu, this will tell us the probability of scoring 0, 1, 2, 3, 4 goals. So Hull City, we expect them to score 0.6 goals. That means, according to that formula, there's a 55% chance they won't score at all, 33% chance they'll score 1 goal, 10% chance they'll score 2 goals, even a 2% chance they'll score 3 goals, which is they won't. Take my word for it, they won't score 2 goals. Manchester United, they expect to score 2.12 goals, so the most likely score is 2 goals, 27. But it's almost the same, only 25% chance of 1 goal, 12% chance they won't score at all, and we're up to a 4% chance they might score 5 goals. Now these distributions actually fit the data very well indeed. And they allow us then to work out the probability, for example, of a 2-all draw. These are assumed independent, so the probability of Hull scoring 2 and Manchester United scoring 2, remember with and, you multiply the probabilities, So it's 0.1 times 0.27, so it's only about a 3% chance of a 2-all draw. So that means we can calculate the probabilities of any outcome. And they're good probabilities, and we can use that to place bets if we want. I don't bet, I don't gamble, I don't recommend it. But if you do want to gamble, use some good mathematics. I don't recommend it, but you can do, it's sort of how to gamble if you must. There's a book called How to Gamble If You Must. So this gives you the probabilities. So it's one of a very important use of a Poisson distribution. Now, I was on the BBC making these predictions. I had to do these predictions. And so, for example, one of the games was Arsenal versus Stoke, and I produced these probabilities that there was a 72% chance of a home win, 19% chance of a draw, 10% chance of an away win, and the most likely result was 2-0 for Arsenal against Stoke, with a 14% chance. So I went through all the matches, producing what was the most likely outcome, and then had to wait for the results to happen. This was terrifying. So, okay, yeah, no, really, 2009, 3 years ago, I had to sit and do this. So, these were my predictions for the scores. These were the most, according to the Poisson distribution, they were the most likely outcomes. And they don't look, for people who know a bit about the score, they don't look very surprising. Yeah, Hull, Manchester United, I thought the most likely was a 2-0 win for Manchester United. So then, you see, what actually happened was, I didn't put any money on these. I mean, I'm not stupid. I don't want to. But some people bet on these. Did put some bets on. Yeah. So this is using statistics. Okay. Arsenal did win. They won 4-1. So I got the result right, not the goal number goals. So Arsenal did win. Aston Villa 1-0. Got it exactly right. Yay! Thank you. Blackburn West 1-1 draw. It was a 0-0 draw, but it's still a draw. Yeah, that was lucky. That was incredibly lucky, because draws are very difficult to predict. That was so lucky. I got that wrong. Everton beat Fulham 2-0 away. So that was wrong. Hull, it was 0-1. Manchester United only scored 1. They weren't playing their best team. That's what they were. Yeah. Liverpool, I said Liverpool would win. Yeah, they won, but 3-1. Manchester City, Bolton, didn't get the score right, got the result right. Sunderland, Chelsea, got the result right, not the score right. Got the result right, got it exactly right. Yeah, look at that, eh? 9 out of 10 right, win, draw, lose, 2 exact scores. So that's using a simple Poisson model. Now, you might think, oh, these are easy to predict, but the BBC man, the expert, only got 7 out of 10 right and one exact score. Yeah, pretty good. So that was great. Unfortunately, they asked me to do it the next year, and it went really badly. Terrible. I think awful. It was a disaster. It was really embarrassing. I was on the radio because I said, "Oh, here's Professor Spiegelhalter," and because I know nothing about football. Okay, so the mathematics of that is that we produced. If you see what we did, we modeled the expectation for a team as a product of terms. We did a sort of A times B times C, where this was something to do with the home advantage, and this was a measure of the attack, and this was a measure of the defense. Now, if we take logarithms, we see this is modeling log mu is log A plus log B plus log C. Now we have a linear model where we're modeling the logarithm of the Poisson mean as the sum of different terms. And those of you who have already done work in linear regression we'll spot that this looks starting to look very similar to a linear regression. And this is what we're going to come to at the end of next week, and the week, well, really suppose the beginning of the week after, we'll be doing Poisson regressions and modeling this kind of count data. So it's a very nice example of a simple, what's known as a Poisson regression. And which is if you Google this, you'll find a lot of information, a lot of use. It's one of the most widely used techniques now in science and in medicine and health and everything. So that's quite nice. So does anyone want wants to have a go at this? They can with their own local football results and see and try to make predictions. If people are interested in football, then it's a good opportunity. Okay, any questions on that? Oh yeah, no, exactly, very good. That was just looking at all the matches that have been played and averaging the total number of goals scored by the team playing at home. So for the season, it was just looking at those totals. So that's just based on it's what you might call an intercept in the model, in the regression model. It's this bit here. And you just get it by looking at the average in the past. So it's estimated from the past data. Yeah, that's a very good point. I had a student, and many people have looked at whether this how well it fits the data. And we'll be coming on to checking whether this actually fits the data. It turns out that a Poisson model fits rather well. But the big assumption is about independence, because it sort of suggests that the teams almost don't play each other, they're playing sort of independently. And of course they're not. And there is some tendency for games to either be low scoring or be high scoring. You know, the pitch on the day, or the sort of something to do with that particular match, it tends to raise or lower the averages. But this isn't a bad model. It's quite good. It's quite good. It does fit the data. Yeah, no, very good. It turns out that if we do this, if we really believe this model, the average is the correct statistic to use. It's the maximum likelihood estimate for this parameter. So if we really believe the model, if the model was wrong, you're absolutely right. You know, in other words, if we had some big score, suddenly somebody scored 15 goals or something like that, that would be very misleading. But that tends not to happen. But it's a good point that just taking the average is only appropriate in a way if the model is correct and it really is Poisson data. Otherwise, you can use more robust methods that are not so influenced by outlying observations. Yeah. That's a very good point. And people have said that, and in fact, the good sports betting companies do use the team's average from previous seasons as well. Because this is saying, no, that's all right. We need to, because that's, in a way, that times that is the team average, or adjustment. The crucial thing is that I'm assuming the home advantage is the same for every team. And that's a big assumption, because some teams have a bigger home advantage than others. They seem to have a bigger effect of playing at home. And I'm not modeling that. That would be an extra subtlety to put in to allow, I'm forcing it to be just a 30% improvement for every team. Yeah, but they're almost the same, they're the opposite. Because you could think of this as an away disadvantage. So it's the same thing, it's just symmetric. Yeah, you could call it something different, of course. Yeah. Oh, absolutely. No, completely right. This is the simplest possible model. This was what was used about 10 years ago by the betting companies. Since then, they've become more sophisticated, and they use recent performance, they use team changes, and they use, this is also just using the whole season, not taking more notice of recent matches than past matches. It's not using previous seasons' data. So you're absolutely right. This is a very simplistic one. And if you really want to bet, you need to be more sophisticated. Yeah. Ah, well, it's because it's count data. Because they will score either 0, 1, 2, 3, 4, 5. So it's a discrete distribution, and it's on the positive integers, essentially. And the Poisson is the natural. It's not always. There are others, negative binomial. There are other distributions that will on the positive integers. But it's if you have a distribution on the positive integers, the natural one to start with is the Poisson distribution. It's not always true, but it's the natural one to start with. Yeah. Exactly. It's all. I mean, this says that football is once you set the average, the game is complete chance. What happens actually during the game is just a whole lot of chance processes, just like molecules bouncing into each other. It's just that there's an overall tendency for one team to be bigger than another. It also means that endlessly talking about particular bits of the game is probably completely pointless. Yeah, exactly. That's what the more sophistication would be working out when it fails. Why did it fail? Do I have to introduce more covariates? Do I have to put in injuries? Etc., etc. Recent data could go in there and could form part of the regression model. Yeah. Now, I must go on, but I want to show you another application in crime. This is a not so amusing one. This was the thing I got involved in London to do with murder in London, homicides in London. Because in one day in 2008, 4 people were stabbed to death in separate incidents in London. And I know that murder rates vary a lot around the world, but in London this was quite a big story. And somebody asked, to have 4 fatal stabbings in one day, could it be a statistical freak? Does that mean things are getting terrible, or could this be just chance? So what I did was get data from the London police of 480 murders in 3 years. These were the London bombings, ones in the bombings in 2005. So I took those out. And on average, there were 160 murders per year in London. 13 per month, 3 per week, 0.44 per day. That's how many there were. Okay. Now, if we assume a Poisson distribution for the number of murders per day, we can just use this mean, just like the football match, to tell us what proportion of days there should be no murders, 1 murders, 2 murders, 3 murders, 4 murders. So it's just like the football match. Just knowing the mean tells you the whole distribution, because the Poisson's only got 1 parameter. So this is a test of, do murders follow a Poisson distribution? We know this is the overall mean. Now, this was the data for every day, how many murders there were in London, whether there's 1, 2, 3, or 4. Or none at all, over these 3 years. Now, so that was the actual, if we assume a Poisson distribution, this is a Poisson distribution with mean 0.44. And that says that over 1,095 days, 3 days, we would expect about 702 days with no homicides, about 300 with 1, about 80 with 2, 10 with 3, and 1 day with 4. So that's the Poisson distribution. That's what we're predicting, what we would see. And this is what actually was the data, which is amazing. The data fits the Poisson distribution unbelievably precisely. So you see, that's the predicted, that's the Poisson distribution. That's the actual observed data. There were actually 713 days with no homicides, 16 days with 3, and 1 day with 4. So once every 3 years, you'd expect there to be, on average, one day in which there's 4 murders in London, completely independent. And that's what fits the data. It's extraordinary. You know, it's like they're just random, I mean, of course, they're not random events, but they're almost as if they're random events. And the Poisson distributions are now being used increasingly for modeling crime, for changes in checking whether crime rates have really fallen, and so on. So this is the official now. We did that analysis, but now the UK government does this analysis for the whole country. So in the whole country, in the whole of the UK, there are 1.78 homicide incidents per day. And an incident, if 3 people are killed, it's only one incident. So there's 1.78 per day in the UK at the moment. And that means that over 3 years, this is a Poisson distribution. This blue one is a Poisson distribution with mean 1.78. So that's what we'd expect. How many days we'd expect there to be no murders, about 170, 300, etc. And the observed data, the purple, fits almost exactly. It was absolutely remarkable. And we will talk about, they do the statistical test, shows no significant difference between the expected and the observed figures. The observed figures are Poisson distributed. And we'll be talking next week about how we can carry out these tests and do such analysis. Okay, so that's not such a cheerful example, but it's amazing that this is, it's as if they're random events, because they're not. Yeah, any questions on that one? No, it's not actually random at all. These have been generally, quite a lot of these will be gangs, they'll be planned, or people in families. It's just that it's mathematically, we're going to find this a lot, that we're applying probability models and mathematics to things that are not really chance. It's just that the mathematical model fits very well. It's as if they're random. If you could think of it, I suppose, like every day, there's 8 million people or something in London. On average, one is killed, one's murdered every couple of days. But, there's 8 million possibilities, each one with a very, very tiny chance of being murdered. And that produces a Poisson distribution. Yeah, exactly. This sort of assumes that everyone's in the same boat. And in fact, of course, it's not. There tends to be clustering. And if you have, it's remarkable that it does fit the data. Well, there's an extension to the Poisson distribution. We'll come on to this, I think, in the 3rd week. What we're saying is that, if I can find it. Right, sorry. The Poisson, you're right, it kind of assumes that everyone's got the same chance. And there's no clusters, but we know. So the Poisson will look like that, or something like that. Assuming you've got almost chance. If they actually cluster, and some people have much higher chance, you tend to get something that's a lot more spread out than the Poisson. And this is known as the negative binomial. And we'll be doing this. It's the distribution on 0, 1, 2, 3 that's wider than the Poisson, because it's got 2 parameters. It's got a parameter for its average, but it's also got a comparator for the spread. The crucial thing about the Poisson, it's only got 1 parameter, which decides both the mean and the spread. But that's absolutely right. In many realistic circumstances, we use this. We use that. And I think, Poisson will be dealing with this later. Okay, are there any more questions? Okay, so that was that. Now I'm afraid we've got to go back to the boring stuff. No, the important stuff. Now we go back to, if I can find it, yeah, fine. Okay. So the Poisson's really important. Oh no, this is quite nice. Yeah, this is getting back to more technical things, I suppose. The mean of a discrete random variable with infinite support. A Poisson is on all the integers from 0 to infinity. So we have to check whether the mean actually exists. Now the mean exists if the sum of the modulus of the observations weighted by their probabilities is less than infinity. Okay, this doesn't always happen. Let me give you an example. Okay, here's quite a nice example. Here's a game. Okay, I'm going to flip a coin, and these don't have heads, do they? What have they got? Animals. What do we find? Do I find an animal? What's that got? Yeah, it's got an animal. A 2-round. It's got a sort of springbok, I think. Yeah, springbok. Okay, so we're going to play a game where I'm going to throw this. Let's call the springbok a head. So I'm going to throw this. If I get, on the first throw, a head, I give you 2 round. Yeah. If I get it on the second one, I give you 4 round. If I do tail, tail, head on the third one, I give you 8 round. If I give it tail, 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 head, I give you 16 round. So I'm giving you 2 to the I, where I equals the first, the first head, the position of the first head. Okay, so there's a good game. So if we were playing this, I would go boom like that, and it's not come up, and it has come up. So I would give you 4 round now for that one. How much will you give me to play that game? Go on, how much would anyone give me to play that game? If I said, I'll play that game with you, how much would you need to pay me? Would anyone do it for, would you give me 100 rounds to do it? No. How much would anyone give me? So how much? 1. No, then I wouldn't play. That's not fair. What's the most you'd give me? That's it. Okay, what's the most you'd give me to play that? It's a good game. You're bound to get 2 back. And you could get a lot more. You could get, if I go up here, you could get millions back. So who would give me, anyone give me 10 rounds to play it? 16? Yeah, okay. Anyone give me 16 rounds to play it? Yeah, mean lot. But let's look at how much you expect to win. How much do you expect to win? To work out that, we have to work out what's the probability of each of these happening. Now, the probability of me getting a head first time is a half. What's the probability of me getting a tail and then a head? What was that? 1/4, yeah. Because it's a half times a tail and then a half. What's the probability of me getting tail, tail, and head? 1/8. It's a half times a half times a half. What's the probability of me getting that? It's 1/16. So in fact, the gamble is that you've got a half a chance of getting 2, a quarter of a chance of getting 4, an eighth of a chance of getting 8. Well, hang on, if we then calculate the expectation, remember, of this random variable, x, the expectation of x is just the amount weighted by the probability. Well, that's 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. It's infinity. So you miserable lot won't give me 10 rounds to play, and yet your expected gain is infinite. You've got an infinite expected amount of money because there's a very small chance I might pay you a huge amount of money. So there's an example of a random variable with this distribution with an infinite expectation. The expectation doesn't exist. And this is known as the St Petersburg Paradox. The fact that we can invent this game with an infinite expectation, but that people are not willing to pay very much to play. And if people who've done economics would recognize it's all to do with diminishing marginal utility of money. The fact that getting 100 times more money is not worth 100 times as much to us. So it's to do with utility functions. But it just shows the real care we have to have about the mean. Now, the Poisson mean is on 0 to infinity, the Poisson distribution, but the mean does exist. And I wanted to run through the proof because it just shows it's a pattern we're going to use a lot in proofs. And the trick, the strategy, is to spot when something is a distribution and therefore adds to 1. So this is just a way of doing the Poisson mean. Okay, so I'm doing this in detail because it's a useful trick. The Poisson mean is the sum between x equals 0 to infinity of x times the probability of x. And so that's not an x, that's a times. Hope you can see the difference. They're not very different, are they? They're a bit different, yeah. Okay, so that's the x times, now, what can we do? We can take one of the mu's outside, and we're left with a mu x minus 1 factorial times e to the mu. And also, because that x, the first one, is 0, we now only have to go from 1 to infinity. The 0 term has disappeared. Now the trick is to look at that and recognize that if we make the transformation from x to I, where I is x minus 1, that just becomes that, it's an identity, because the infinity is still infinity. And now we see that's a Poisson distribution. So it adds to 1, because distributions add to 1. Isn't that cool? So that all goes out, and we're left with the mu. A very standard trick, and we're going to be using that trick a lot, of recognizing things are distributions, and then suddenly being able to do, in this case, summations, but when we do, later on, it'll all be integration, and we'll spot that. So learn the trick, it's a good trick. Okay, so that's nice. And then you could also, in your spare time, work out the variance, why the variance of a Poisson is also mu. Oh, there's a nice question. If you get bored, yeah, okay, here's some questions for you to do if you finish everything else after the break. Prove to me that the variance of a Poisson is also mu. So you can prove that. That's a nice one. Using a similar trick. Okay. This one, I've rubbed it off. This, what I've just rubbed off, this distribution here was the waiting time till the first head. And this is just a special case of what's called a geometric distribution. Beautiful distribution. You can do all sorts of things with this. The geometric distribution is the waiting time until the first success in a series of Bernoulli trials. Now, we can immediately see the form of this distribution, because if the first event, the first success, happens in position x, so the probability that x equals x equals the probability that there was a failure, and then another failure, and then another failure, and then finally a success. So there were x minus 1 failures and then 1 success. Because that's what must, just like on the coin, you do failure, 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 and then success. So that means we derive immediately that the density is 1 minus p to the x minus 1 times p. Now that has expectation 1 over p. Now, so there's your next job. Actually, no, this is one comes first. Prove that, that's number 2. Number 1, prove that the expectation of a geometric is 1 over p. So what I want you to do is prove, if you've got time, if you feel like it, that the sum of x, 1 minus p to the x minus 1 times p, between x equals 1 and infinity, equals 1 over p. And maybe that's a familiar problem to some of you, but it's there's at least 2 different ways to do it, but that's quite a nice problem. It's interesting, the 1 over p is quite intuitive, but not that easy to prove. Not straightforward to prove. Okay, so, right. The last few slides now are, I'm afraid, are just, in a way, things to learn. Yeah, they're just things that are really useful that we use again and again. So I'm just going to go through them and say, and for you to refer back to. These last slides are useful to refer back to. So the first, these are just very useful things that we will use again and again. So just, the first is, if we've got random variables, what happens if we add something to them? So expectation of c plus x, well, that just comes back into there. If we break this up into 2 additions, this adds up to 1, and we get c plus expectation of x. So you can think of it as just a linear transformation of the variable, also does exactly the same change to the expectation. In contrast, the variance, if we add a constant to a variable and calculate its variance, the c's cancel out. And it makes no change to the variance. Sorry, yeah. Oh, any scalar constant.
What does it mean?
Oh, no, it just stands for any number, any scalar. So 3, any number at all. So it's just a scalar quantity, just a quantity. So it could be anything. So what this is saying is that if we've got a distribution, we're doing discrete distributions at the moment, if we add c to it, move it all along, obviously the position changes, but the spread does not change. So that's the intuition. Now, the multiplication, if we multiply everything by c, then we multiply the expectation by c as well. So if we spread this, if we multiply this up by something, if this goes out, the expectation is multiplied, but now the variance goes up as the square of the multiplier. And it's very easy to forget. The variance of a multiplier times x, scalar times x, is the square times the variance. The variance is always on a squared scale. It means that the standard deviation, the square root of that, does multiply by c, which is nicer. Okay, so it's simple first rule. Next rule we're going to use quite a lot when we want the expectation of a general function of a discrete random variable. A one-to-one function y is g of x. How do we calculate its expectation? Well, it's just defined like that. So all we do is put it in and weight it by the probability of x. But there is an alternative method in which we actually try to find the distribution of g. So that, or y. Y is g of x. We actually find the distribution of y. And that's quite easy to do because the probability that y equals y is just numerically the same as the probability that x is g to the minus 1 of y. So we're going to return to this. This isn't, when we do, tomorrow when we do continuous random variables, this becomes a bit more complicated, the change of variable. but it is quite important, so we'll have to do it, I'm afraid. Okay, so that's just for reference as well. How long ago? Oh yeah, we can carry on a bit more. The last few tedious slides. Oh yes, this is important. This is to do with joint distributions of two variables, pair of discrete random variables. We just define the joint distribution as the probability that x equals x and y equals y. And then we can get a conditional distribution, which, remember the definition of conditional probability, it just follows immediately that this is our definition for distributions. The probability of x given y is the joint distribution divided by f of y, if it exists. So that's so straightforward. This one is really important. This is this idea of what I called before extending the conversation, that the distribution for the density for a variable x, we can take the joint density over two variables and just add up over the values of y. Which also, by that rule there, is equivalent to this form, where we condition on y times f of y, because that is just equal to that, and then add up over y. Again, we're going to be using this a lot when we come to Bayesian methods, and in using integration. It'll be using integration. Now, the first, which we had before, applied to events rather than random variables. X and y will be mutually independent if the joint distribution factorizes, the joint density factorizes. And finally, I hope, is that the last one? Yes, thank goodness for that. So as I said, these are all rather dull reference things, just so they're there for you to look at. What about happens if we have two random variables, x and y, not necessarily independent? Now, the variance of x plus y is just the expectation of x plus y minus the expectation of x plus y and the whole lot all squared. We can rearrange this to give this all squared, and then we multiply out the square, and the first bit, where we have expectation of the square of that, is just variance of x, and then we have a variance of y. But then we got the cross product terms, and we end up with this thing. Oopsie. And that's known as the covariance of x and y, which can also be written, and is usually written in this form. So the covariance of x and y is the expectation of the product minus the product of the expectations. Now, if these are independent, this is 0, and we have this nice form that the expectation of the product is the product of the expectations, because this cancels out to make 0. The converse isn't true. You can have a 0 covariance even if they're not independent, because this only really measures a linear relation. And finally, last thing before we stop, the correlation is the covariance divided by the square root of the product of the variances, which is just the product of the standard deviations. Okay, any questions on this immensely tedious and boring things? I dare you to ask any question. But they must be done, I'm afraid. Yes. Oh, additional assumptions. Yeah, I've assumed, at the moment I've assumed 1-to-1.
X equal to G1 as 1 or
Yeah, I'm assuming a 1-to-1 transformation that can be inverted. Yeah. It's a good question, because when I was writing that, I thought, whoa, hang on, surely it doesn't have to be 1-to-1, because I might have a many-to-one, a mapping onto a smaller space. So I think I've done a rather restrictive assumption there, and I think you could be a lot more general. Good, very good. Because when I was writing that, I thought, oh, what about this? Maybe this goes to more than 1 point. And what I really mean is x, what I should have written is the probability of x equal any value of x that satisfies that relationship. Yeah, so it doesn't have to be one-to-one. Yeah, exactly. So, yeah.
Slide number 14.
Slide number 14, yep. You just do it, just examples. You just have examples to show the converse doesn't hold. And the simplest ones I always remember is when I'm just using data. If you have, because essentially covariance measures a linear relation. And so if I have if I have some distributions here, so let's do a discrete distribution. If I have a distribution like this, here's x and here's y, and each of these points here is equally likely to occur as a distribution. The covariance between those is going to be 0. If I calculate the covariance, but there's a very strong, they're not independent at all. There's a very strong relationship between them, but the actual correlation and covariance, if I do the calculations, will be 0. So the point is that these only measure sort of linear relationships between. And if you have a non-linear relationship, you can get these sort of paradoxes. So you prove it by finding a counterexample. And I will maybe find a better one than that. Yeah. Yes. Well, it's suppose it's just it's defined as this. You know, it's how things co-vary. I mean, well, the point is, well, certainly if you can prove they're independent, that the joint distribution factorizes, then you know that the covariance will be 0.
What do you mean by independent?
Oh, independent, that's just that if you can show that, if you've got two distributions and you can prove mathematically that the joint distribution factorizes into two terms, so that implies that the covariance of xy equals 0, because they're independent. So if you can show they split, that it factorizes, then the covariance will be 0. But that doesn't, the inverse isn't true. Okay, any more, right. Right, okay, well, let's have a break, and then if we go, might as well go upstairs, there's things left from yesterday, in particular, learning about this random dot binomial function to be able to generate from it and use it to plot, have we done plotting? Can we plot? It would be really good. I mean, okay, here's a real challenge. It would be great if we could produce things like that. Do you know how to do it? I don't. I have no idea. We haven't done it. Well, anyone who's really keen, because we will want to be doing plotting. By the end of the week next week, we really want to start plotting distributions. You know, look at the normal distributions. We want to be able to see the things. It's really important to be able to see them. So any advance you can make on plotting would be great. Really useful use of time. And anyone who much prefer doing maths, try that one. Maybe you know the tricks, but I really like that one. These two, if you want to, if you just want to sit there with a pencil and paper, that's fine as well. Okay. Right. Thanks very much indeed. Let's go. Was that better? I tried to be a bit slower. I'll try even more. I am sorry. I get excited.